Okay, so in section 8.2, we're going to look at hypothesis testing of a single mean. And this is going to be the case where sigma is known. Okay, so we talked in the last section about some key things. Right now, we're going to go ahead and just go in through our 4-step process to conduct a hypothesis test. So let's go ahead and there we go. Okay. So here's example 814 here, and you could pause it and if you want to kind of take a second and read through it. But the key thing is that we know 16 is less than 16.43, but is it significant? That's really the key question that we want to answer here. Is it significantly less here? So Jeffrey has a mean time, he has those goggles, he performs better, but is it noticeable? Is 16 so far away from 1643 that it makes a big difference? And that's kind of the key question we want. So our first step here is going to be to identify the hypothesis. So the null and alternative, and I'm going to kind of abbreviate a little bit here. Hypothesis here. So HOHA. There's my null, there's my alt. I like to label all of that. And what we're looking at here is we're looking at actual means. So we're looking at a mean time here. And that's going to tell us that we're doing mu. Okay. So let me write that down. So note that we are talking mu, not proportions or even standard deviations, which we'll look at in a bit as well. And so we want to know if this mean time is going to be less than 16.43. So, because that's actually what he's saying here. Frank thought that the goggles helped Jeffrey swim faster than 16.43 there. Okay, so faster meaning it's going to be less time. Since we're in a race, less makes it faster. And then our null is going to get 16.43 there. And I always like to identify the claim. That's whatever the information it's giving us. We're going to use that a bit later when we do our decision. And if you recall, the null could only take on the equals. The alternative could have not equals, less than, or greater than. And that's how I decided which to put where. So our second step here, we're going to go ahead and look at the statistics here and kind of the data. And let's pick apart this problem of what we have. And so X bar and sigma and alpha here. And so X bar is going to end up being the time he took. And so this is going to be from our sample. Notice X bar here is going to be the sample there. So from the 15 swims there, he had a time of 16 seconds. Okay. So X bar is the mean of the samples here. If you recall, mu is the mean of the population. That's kind of what we're trying to make an educated guess for. So what we have is our X bar. Our sample size is going to be 15. And then the main question here is S or sigma, who's given, right? Is sigma given in this case? And the answer here is going to be yes, it actually is given. This one's very nice because it specifically states the population standard deviation. So it's going to go ahead and give that to us of 0.8 seconds. And it also gives us our significance level, our alpha, which is 0.05. And some common values are 1%, 5%, or 10%, or in decimal form, 0.1, 0.5, and 0.10. If for some reason it does not give you a significance level, you're allowed to pick any of these, but typically we'll pick the middle value, the 0.05 in this case. All right, so let's go ahead and look at step 3 here, which means we're going to graph and do our calculations here. So let's always do our sketch and let's label everything. So right in the middle here is going to be our mean. So what we're assuming this mean to be, so 16.43 right here. And notice this is time in seconds. We're going to label this x-axis a couple of ways here. So this is with the actual units, but we could also talk about it in terms of z-scores, and that's going to be very important. If we're talking z-scores, then right in the middle is going to be 0. Our mean is going to be 0 in that case. And we want to label our significance level here, or the critical region. So right in here, we're going to have our alpha, which is 0.05. And the question is it a right-tailed? Is it a left-tailed? Right, which are we actually going here? And so, sorry, this one's going to be a left-tailed because our HA is less than in this case here. So whenever it's less than, it's going to be left-tailed. If it's greater than, then we'll have right-tailed. Or if it's not equal, then it could be a two-tailed. And we'll look at some examples of that. But that's how I need to shade off to the outskirts. Where about exactly? I don't know. I'm just kind of giving a guess there. And my alpha is 0.05. Now, that specific corresponding z-score there is what we're going to call the z critical value, or z alpha, as some textbooks denote it there. So that's z critical value here. And in order to get that critical value, we did this kind of in the last chapter, it's really just an inverse norm function of area to the left, and then the mean and the standard deviation. And since we're using the standard norm or we're talking z-scores, it's going to be 0, 1. We could actually use a table backwards as well to get those values, which we'll look at in a bit. But it's really just an inverse norm function here. And that's going to give us negative 1.65. So that's a z-score, what we're going to call the critical value. So we want to calculate another z-score here, which is going to be the test statistic here. And so this test statistic is going to be dependent on the sample. So the z-test statistic here. And if you recall the formula for a z-score, x bar minus mu divided by a sigma over the square root of n there. And we're just going to go ahead and plug these values in. So 16 minus 1643 all over 0.8 divided by the square root of 15. And if we calculate that, that z-score, that z-test statistic is going to give you approximately negative 2.08 or so. Okay. So we're trying to compare these two z-scores. That's really the bottom line here. We calculate these values and then we could place these guys. And so here's our critical region that corresponds to the alpha. And so my test statistic, since it's negative 208, it's smaller than negative 165. So I'm looking at the comparison of this value and this one right here. And so that's how I need to place the test statistic to the left of the critical value there. So it falls inside of that critical region. So alpha is the area associated with that critical value. Well, then that test statistic is also going to have some area associated with it. We're going to call that the p-value. And in order to get that p-value, since we want to get area there, well, that's actually a normal CDF. So if you recall, kind of going towards infinity, or what we're calling a negative E9 there, or negative infinity, right, to negative 208 and then 0, 1. And on the next slide, I'll show you how to work this out by hand, but just to kind of move through this example here to get the gist of it. So that area that corresponds with the test statistic, it's just a normal CDF, which we did in the last chapter. And so that p-value is going to be approximately 0.019. Okay. And so if we're talking actual times, that corresponds to the time of 16 seconds there. But its z-score is negative 208. Okay. So again, this one marker here, we could think of that in terms of the area from that line, the z-score, or the actual units. And we want to be able to go back and forth between those. And so we're going to use z-test in this case because we do know our sigma. Our sigma is actually given here. And if we plugged in that a Z-test and we run this, a lot of these calculations will also end up coming out. But just so you could kind of see where some of this is. So it's going to give you that actual test statistic, and you can look at the tutorial on how to run a Z-test afterwards. But it's going to give us that. So we're not even going to have to do a lot of these computations. Even if you are doing some stuff by hand, that Z-test will go ahead and do a lot of these calculations. So then we want to talk about our discussion and our conclusion here. And so in short, if your p-value is less than your alpha, then we're going to say that we reject the null. If your p-value is greater than the alpha, then we do not reject. And so the reasoning being that alpha is a very small amount. That's kind of like our error there. It's a very small amount. So think of the outskirts as very unlikely, right? A very small probability in that case. So if you have a small probability, it's kind of unlikely, so we're going to reject. Versus if that test statistic falls outside the critical region, for example, if it was somewhere over here where there's high probability, then it's kind of more likely, so we do not reject. And this is always for the null. Another way is to compare the z-scores here, and we're just trying to see if it's in the critical region or not. Typically, if you're doing things by hand, the z-scores are better to compare. If you're using technology, since they give you the areas, it's easier to compare the p-value with alpha. Okay, so if your p-value is less, we're going to reject and all. That's if it's in that critical region. And so p-value is greater, we do not reject. So in this case, our p-value is going to be smaller because it's less area, so we would assume for it to be contained within that critical region. So we're going to reject. We're going to reject the null. This test is always for the null. And so this is where we're going to go back over here. If we reject the null here, then the alternative, we're going to say that we do not reject. And since the alternative is the same as the claim, we do not reject. And that's why I like to put that note of the claim there, because it helps us out in this process here. So we do not reject. Since the alternative is our claim, we are allowed to say we support. In the last section, there's that diagram table that tells you how to write up the conclusions. And so that's where I'm getting this prompt. So there is, we could say there is sufficient evidence to support the claim that the goggles help Jeffrey swim faster than 16.43 seconds. Okay, so let's look at how we actually came up with some of this with this p-value right up in here using the actual charts. Okay, so the key thing is when you're using one of these tables, always look at the pictures. It's always a good idea to have your pictures lined up. And we could see from the picture that some of them have area shaded on the left below the halfway point right here, and others have it going over that halfway point there, and some even shade the middle region. So whichever chart you're using, make sure that it matches up with the actual picture that you have. And so in this case here we have on the left negative z-scores, and then on the right we're going to end up with positive z-scores. Okay, and so our test statistic was negative 2.08. And so on our z-score here, we're going to go ahead and do the first decimal of accuracy on the left, so that negative 2. And then we're going to go to this the second decimal of accuracy. So one does the first, one does the second here of that 0.08. And we're just going to see where these guys match up there. And it's roughly about 0.0188. Now, these are tables that we're using. They're approximations. Your technology is going to be a lot more accurate. So a lot of times if you are checking a specific textbook or so in the back of the book, you might be off on the third or fourth decimal, depending if they use tables or if they use technology to give those solutions. But if you're accurate to about 3 decimals, probably did it correctly there. So this is equivalent here to doing a normal CDF from negative E9 to negative 20801. And we got approximately 0.019 or so. And so that's where that p-value came from that we had calculated earlier. Now again, if you're plugging it into your calculator, it's going to spit out the test statistic and the p-value. So you're not going to need to plug in and or calculate any of that. It'll give you both of those. But if you are doing it by hand, you'll need to calculate the z-score formula and then use the table in order to get that. Okay, so here's another example. If you want to go ahead and pause it and give this a go, and then I'll go ahead and work it out. And it's asking us to use a TI here or some technology, so we're going to go a little bit heavier on that and not get so much into the formulas. Okay, so first thing is the null and alternative hypothesis here. So HO and HA, the null and alternative, and we're talking means, okay? So we could throw, so right at the beginning, the mean throwing distance there for that one. So it's kind of a giveaway. It's just giving us that directly. And it's saying that it's going to be greater than 40. The Marco could toss it larger, further than 40 yards right here. Marco can throw further than 40 yards there. So that's the actual claim there. And then so we have our null. Second step is going to be our stats here, and let's see if we could identify everything. So our mean from the sample that we had here from those 20 throws there, and then is going to be 45 yards. And then the question is sigma or S given to us? Now this one isn't as nice where it specifically said a population standard deviation, or it didn't denote sigma. But it tells us that the mean throwing distance of Marco for all his football, so they're looking at everything, his whole past record. So they're implying that that ends up being his, that standard deviation is to the population, because it's not from a sample. It's kind of from all of his throws together. So you want to be cautious about that. Sometimes questions are not that specific, but it is giving us sigma of 2. And our alpha we're going to use here is 0.05, so that's given. And then we are going to go ahead and go to our next step, our graph and calculations. And I highly urge you, even if you are using technology, make your sketch first so you know where everything is, and then that'll help you out afterwards. So make sure you're able to label this. So our means 40 there, and this is yards. And again, we could talk about this in terms of z-scores as well. So that's talking about 0, and I'm going to label my alpha, my critical region, and I know this one is right-tailed because it's greater than this time here. So alpha is 0.05, and that corresponds to a z-score of our critical value, z-score there, or what they call z-alpha sometimes. And so our z critical value goes with alpha. Those two go together. If you do a normal CDF or an inverse norm of those two, they're going to go back and forth. And then, okay, so then the z-test statistic, that goes with the p-value. So again, if you do a normal CDF or inverse norm of those two, those are going to go back and forth. And we're using a z-test here, and I'm going to go ahead and plug that into the calculator, and I'll go ahead and put some directions for that on the next page, and there'll also be a video for that. So once we run a z-test, that's going to give us a test statistic of 11.10, or you could use a formula from the previous example. And it's going to also give you a p-value. And now the p-value is not really 0. We're rounding to about 4 decimal places, so it's very, very small. Our alpha is 0.05, and let me label that p-value there. So it's going to be just that little area right inside there. So very, very small amount in there. That's the p-value. And then the critical value, we either use our tables backwards. So getting the area inside, or you could do an inverse norm. And that's going to give you 1.65 there. And again, area to the left is going to be 95. Since you have 5 to the right, you have 95 to the left. That's the complement of that. And there's your Z test statistic and your Z critical value. And if we're talking yards, that test statistic corresponds with that 45 there. And so the question we're asking, is that 45 so much larger than 40, right? That it significantly makes a difference there. Okay. So our p-value less than alpha. So we're going to reject the null. So we do not reject the alternative. So again, going here, if we reject the null, that means we do not reject the alternative. And since the claim is also your alternative, we're going to make the same decision as that. Key note, the claim is not always the alternative. It's able to go back and forth. And we'll look at some examples of how that changes as well. So we would say there is sufficient evidence to support the claim that Marco can throw the football, or throw further, right, than 40 yards by adjusting his grip in this case. Okay, so the question here is, again, not that he threw further. We know he threw further, but you know, is 1 yard further good enough? Is 2 yards further, 3 yards? Where exactly is that line in the sand? And so this critical value here, that is our line in the sand, right? Any value right in here is going to be close enough to 40 where we know it's larger than it, but it's close enough where we say, they're about equal. And so we want to know where is a value that you go over it where we would say, hey, now it's a big enough difference. And that's what that critical value is doing. It's our cutoff. So the test statistic here, we're trying to just compare that z-score. Does it fall beyond that marker or not? And if it falls beyond it inside the critical region, right, then we say that we reject the null. And you could also do the comparison by looking at the areas. If your p-value, if this area is less than alpha, then it has to be contained within that critical region. And so it's going to be inside. So whether you're looking at z-scores or the areas, we're just trying to see, when we draw our line in the sand here, is that value, that test statistic, beyond that? Okay. So we'll start looking at some other hypothesis tests, but let's go ahead and, but I first wanted to look at here. There we go. Okay, so here are some directions up on how to do the calculator. You can look at the video that'll be posted, but here are just some written directions. And I wanted to remind us also where the conclusions are coming from. So how we do our write-up, these are the 4 choices there. You could review that from the last section. And then also our 4-step process for the hypothesis test there.